Imagine waking up tomorrow morning, but instead of your coffee cooling down, it suddenly becomes hotter. Instead of your newspaper aging and yellowing, the ink becomes fresher and more vibrant. Instead of remembering yesterday's events, you find yourself forgetting them as if they're being erased from your mind. This isn't science fiction. This is what our universe might look like if time flowed backward. We live in a world where time seems to have a clear direction. We age, we remember the past but not the future, and we watch ice cubes melt in our drinks. But what if I told you that the fundamental laws of physics don't actually require time to flow forward? What if the equations that govern our universe work just as well when time runs in reverse? The question of time reversal isn't just a philosophical puzzle. It's a real scientific inquiry that challenges our most basic assumptions about reality. When physicists peer into the quantum world or examine the mathematical foundations of our universe, they discover something startling. The deepest laws of nature show no preference for forward time over backward time. Think about a movie played in reverse. A diver springs up from the water and lands perfectly on a diving board. A broken vase reassembles itself from scattered pieces. These scenes look strange to us, but they don't violate any fundamental physical laws. They only violate our everyday experience of how things usually happen. This leads us to one of the most profound questions in physics. If the universe doesn't have a built-in preference for time's direction, why do we only experience time flowing forward? Why don't we see coffee spontaneously heating up or broken eggs reforming themselves? And perhaps most mysteriously, if time were flowing backward right now, would we even notice? To understand these questions, we need to dive deep into the physics of time itself. We need to explore the hidden symmetries of nature, understand why entropy creates time's arrow, and discover what it would really mean for time to flow in reverse. The answers will challenge everything you think you know about the nature of time and reality itself. To understand whether time can truly flow backward, we must first examine what the fundamental laws of physics actually tell us about time. And here's where things get fascinating. When we look at the most basic equations that govern our universe, we discover something remarkable. Time reversal symmetry is not just possible, it's built into the very fabric of reality. Let's start with Newton's laws of motion, the foundation of classical physics. When Isaac Newton formulated his famous equation, F equals mr, he unknowingly created something that works perfectly, whether time flows forward or backward. Imagine a simple pendulum swinging back and forth. If you were to film this pendulum and then play the video in reverse, the reversed motion would look completely natural. The pendulum would still obey Newton's laws perfectly. There's no way to tell from the physics alone whether you're watching the original video or the reversed one. This isn't just true for pendulums. Consider a planet orbiting the sun. If time suddenly reversed, the planet would simply orbit in the opposite direction, tracing the exact same path but backward. The gravitational forces would remain the same, the orbital mechanics would be identical, and Newton's equations would be satisfied completely. The mathematics doesn't care which direction time flows. This symmetry extends far beyond simple mechanical systems. Maxwell's equations, which describe electromagnetism and light, also exhibit perfect time reversal symmetry. Light waves can propagate forward or backward in time with equal validity according to these fundamental equations. An electromagnetic wave traveling from point A to point B is mathematically identical to a wave traveling from point B to point A if we reverse the direction of time. Even more striking is quantum mechanics, the theory that governs the microscopic world. The Schrödinger equation, which describes how quantum systems evolve, is completely symmetric under time reversal. If you have a quantum particle in a particular state, the equation that describes its future evolution is mathematically identical to the equation that would describe its past evolution if time were running backward. This creates a profound puzzle. If a quantum particle can exist in a superposition of multiple states, and if the equations work equally well forward and backward in time, then there's no fundamental reason why we couldn't have quantum superpositions that extend backward in time as well as forward. The mathematics treats both directions as equivalent. Let's consider a more concrete example. Imagine two billiard balls colliding on a perfectly smooth table with no friction. The collision follows precise physical laws. Now, if you were to reverse time at the moment after collision, the balls would retrace their paths exactly, moving backward to their original positions with their original velocities reversed. Every aspect of this reversed motion would be physically correct according to the fundamental laws. This principle extends to more complex systems as well. Consider the motion of gas molecules in a container. Each individual collision between molecules follows time-reversible laws. If we could somehow reverse the velocity of every single molecule simultaneously, they would all retrace their paths perfectly, eventually returning to their exact starting configuration. The implications are staggering. According to fundamental physics, there's no preferred direction for time. The universe could run backward just as easily as forward, and the basic equations would remain satisfied. This suggests that our perception of time's arrow isn't built into the deepest laws of nature. But this raises an even deeper question. If the fundamental equations are time-symmetric, why do we observe such a strong directional flow of time in our everyday experience? Why don't we see broken glasses spontaneously reassembling, or smoke flowing back into fires, or people growing younger instead of older? The answer lies in understanding that while individual particles and simple systems obey time-reversible laws, complex systems with many particles behave very differently. When you have trillions upon trillions of particles interacting, statistical effects begin to dominate, and these statistical effects create the arrow of time we observe. Consider our billiard ball example again, but now imagine not two balls, but a trillion balls, all moving randomly. While each individual collision is time reversible, the overall behavior of the system becomes directional. The balls will tend to spread out, to become more randomly distributed, to lose their organized motion. This is the beginning of entropy, and entropy is what creates time's arrow. The time symmetry of fundamental physics also appears in some surprising places. In particle physics, there's a deep principle called CPT symmetry. This states that if you simultaneously reverse charge, parity, and time, the laws of physics remain unchanged. This means that an antiparticle moving backward in time behaves exactly like a normal particle moving forward in time. This insight led physicist Richard Feynman to propose a radical interpretation. He suggested that antiparticles are actually ordinary particles moving backward in time. When we observe the creation and annihilation of particle-antiparticle pairs, we might actually be seeing a single particle moving forward and backward through time, creating what appears to be two particles to our forward time perspective. Even in the realm of general relativity, Einstein's theory of gravity and space-time, we find time symmetry. The Einstein field equations that describe how matter and energy curve space-time work equally well whether time flows forward or backward. A black hole forming from collapsing matter is mathematically equivalent to a white hole expanding and emitting matter, just viewed in reverse time. This fundamental time symmetry raises profound questions about the nature of reality itself. If the deepest laws treat forward and backward time equally, then our experience of flowing time might be more of an emergent phenomenon than a fundamental feature of the universe. Time might not flow at all in any objective sense, but rather our consciousness might create the illusion of flow by moving through a static, four-dimensional space-time. The mathematical elegance of time reversal symmetry suggests that our universe possesses a deep underlying balance. For every process that can occur forward in time, there's a corresponding process that can occur backward in time. This symmetry connects to some of the most profound principles in physics, including conservation laws and the fundamental structure of space-time itself. The implications of time reversal symmetry extend into even more exotic realms of physics. In quantum field theory, the mathematical framework that unifies quantum mechanics with special relativity, time reversal symmetry plays a crucial role in understanding the creation and annihilation of particles. When particles pop into existence from the quantum vacuum and then disappear again, these processes are completely time reversible at the fundamental level. Consider the strange world of virtual particles, those ephemeral entities that constantly appear and disappear in empty space. According to quantum field theory, these virtual particles are constantly being created in pairs, existing for incredibly brief moments before annihilating each other. But here's the remarkable thing: if time were reversed, these same processes would occur in exactly the same way. Virtual particle pairs would still appear and disappear, just in the opposite temporal order. This symmetry becomes even more fascinating when we consider particle accelerator experiments. When physicists smash particles together at enormous energies, they create showers of new particles that then decay into other particles. Every single one of these processes, from the initial collision to the final decay products, follows time-reversible laws. If we could somehow reverse time at any point during these experiments, all the particles would retrace their paths exactly, eventually recombining into the original colliding particles. The Large Hadron Collider, the most powerful particle accelerator ever built, regularly demonstrates this time symmetry. When protons collide at nearly the speed of light, they create exotic particles like the Higgs boson, which then decay into more familiar particles like electrons and photons. But according to the fundamental equations, this entire process could run in reverse. Electrons and photons could spontaneously combine to create a Higgs boson, which could then decay back into the original protons. Of course, we never observe such reverse processes in practice, but this isn't because they violate fundamental physics. Rather, it's because of the astronomical improbability of all the particles happening to have exactly the right positions, velocities, and quantum states to reverse the process. This brings us back to the central mystery: why statistical effects create a preferred direction for time, even when the underlying laws are symmetric. The concept of time reversal symmetry also appears in the study of crystalline solids. The equations that describe how atoms vibrate in a crystal lattice are completely time symmetric. If you could reverse the motion of every atom in a crystal simultaneously, they would all retrace their vibrational paths perfectly. This symmetry is fundamental to understanding how crystals conduct heat and electricity. Even the propagation of sound waves through materials follows time-reversible laws. A sound wave traveling through air or water could, in principle, reverse its direction and retrace its path exactly if time were reversed. This principle is actually used in some advanced acoustic technologies, where engineers create time-reverse sound waves to cancel out unwanted noise, or to focus sound energy at specific locations. In the realm of optics, time reversal symmetry manifests in fascinating ways. Light rays traveling through complex optical systems, bouncing off mirrors and refracting through lenses, follow paths that are completely reversible. If you could reverse time at any point along a light ray's journey, it would retrace its path exactly, emerging from the optical system in precisely the opposite direction from which it entered. This optical time reversal symmetry is more than just theoretical. Scientists have actually built devices called optical phase conjugate mirrors that can create time-reversed light waves. When a complex, distorted light beam hits one of these special mirrors, it reflects back a beam that retraces the original path exactly, automatically correcting for all the distortions it encountered on its way to the mirror. The symmetry extends to electromagnetic fields in general. Radio waves, microwaves, and all other forms of electromagnetic radiation follow Maxwell's equations, which treat forward and backward time identically. A radio signal traveling from a transmitter to a receiver could, in principle, reverse direction and travel back to the transmitter if time were reversed. This has profound implications for our understanding of causality and information. If electromagnetic waves can propagate backward in time just as easily as forward, then the traditional notion of cause and effect becomes more subtle. Information encoded in an electromagnetic wave doesn't have an inherent temporal direction according to the fundamental equations. Even gravity, our most familiar force, exhibits perfect time reversal symmetry. Einstein's general relativity equations work identically whether time flows forward or backward. A gravitational wave rippling through space-time would create exactly the same distortions whether it's propagating into the future or into the past. The recent detection of gravitational waves by LIGO has opened up new possibilities for testing these time symmetry principles in the realm of gravity. The mathematical structure underlying all these symmetries is deeply connected to conservation laws through Noether's theorem. This fundamental principle states that every symmetry in physics corresponds to a conservation law. Time translation symmetry leads to energy conservation. Spatial translation symmetry leads to momentum conservation, and time reversal symmetry connects to the conservation of certain quantum numbers and the fundamental stability of physical processes. Yet despite this mathematical beauty and fundamental symmetry, we're still left with the central mystery that dominates our everyday experience. If time reversal is so fundamental to physics, if it's built into the very equations that govern reality, why does our macroscopic world show such a clear and unwavering preference for one direction? Why don't we see the time-symmetric processes that the equations allow? The answer to this puzzle will take us into the realm of thermodynamics and entropy, where we'll discover how statistical mechanics creates the arrow of time from the time-symmetric laws beneath. We'll see how the behavior of vast numbers of particles creates emergent directional behavior, even though each individual particle follows time-reversible laws. Now we come to the heart of the mystery. If the fundamental laws of physics are perfectly symmetric in time, why do we experience such a strong directional flow? Why don't broken eggs spontaneously reassemble themselves? Why doesn't spilled coffee flow backward into the cup? The answer lies in one of the most powerful and universal principles in all of science, the second law of thermodynamics and the concept of entropy. Entropy is often described as a measure of disorder, but this simple definition barely scratches the surface of its profound implications for the nature of time itself. More precisely, entropy measures the number of different microscopic arrangements that can produce the same macroscopic state. And here's the crucial insight. In any isolated system, entropy always increases over time. This is the second law of thermodynamics, and it's what creates the arrow of time we experience in our daily lives. Let's start with a simple example that illustrates this principle beautifully. Imagine a container divided in half by a removable barrier. On one side, we have 100 gas molecules. On the other side, we have empty space. Now we remove the barrier. What happens? The gas molecules spread out to fill the entire container. This seems natural and inevitable to us, but why? The answer lies in probability and statistics. When the 100 molecules are confined to half the container, there's only one way to arrange them. They must all be on one side. But when they're free to move throughout the entire container, there are an enormous number of different ways to arrange them. The molecules could be distributed 50-50 between the two halves, or 60-40, or 90-10, or in countless other configurations. Here's the key insight. The vast majority of these possible arrangements have the molecules roughly evenly distributed throughout the container. Only a tiny fraction of the possible arrangements have all the molecules clustered on one side. So when the molecules move around randomly, they're overwhelmingly likely to end up in a more evenly distributed state, simply because there are so many more ways to be evenly distributed than to be clustered together. This is entropy in action. The initial state with all molecules on one side has low entropy because there are very few ways to arrange it. The final state with molecules spread throughout the container has high entropy because there are many, many more ways to arrange it. The second law of thermodynamics tells us that isolated systems evolve from low entropy states to high entropy states, and this evolution defines the direction of time's arrow. But here's where things get really interesting. There's nothing in the fundamental laws of physics that prevents the reverse process from occurring. In principle, all 100 molecules could spontaneously move back to one half of the container. This wouldn't violate Newton's laws, or quantum mechanics, or any other fundamental principle. It's just extraordinarily, mind-bogglingly unlikely. How unlikely? Let's do some mathematics. The probability of all 100 molecules spontaneously clustering on one side is approximately 1 in 2 to the power of 100. That's roughly 1 chance in 10 to the power of 30. To put this in perspective, this number is larger than the total number of atoms in the observable universe. The probability is so small that even if we waited for billions upon billions of years, we would never expect to see it happen even once. This statistical understanding of entropy helps us understand why we never see macroscopic time reversal in our everyday experience. It's not that reverse processes are impossible, they're just so improbable that they never occur in practice. A broken egg could spontaneously reassemble itself without violating any fundamental law of physics. But the probability is so astronomically small that it would never happen even if we waited longer than the age of the universe. Let's consider another example that drives this point home. Imagine you have a deck of 52 playing cards arranged in perfect order, ace through king in each suit. Now you shuffle the deck randomly. What's the probability that after shuffling the cards will still be in perfect order? It's 1 in 52 factorial, which is approximately 1 in 10 to the power of 67. This number is so large that if you shuffled the deck once every second since the beginning of the universe, you still wouldn't expect to see the ordered arrangement appear even once. This is exactly analogous to what happens with entropy in physical systems. The shuffling corresponds to the random thermal motion of particles, and the ordered arrangement corresponds to low entropy states. Just as shuffled cards tend to become more disordered, physical systems tend to evolve toward higher entropy states. The concept of entropy also explains why we have such a clear sense of the direction of time. Our memories are physical structures in our brains, and the formation of memories is an entropy increasing process. The chemical reactions that encode memories, the growth of neural connections, the organization of information in our brain cells, all of these processes increase the total entropy of the universe. This means that our perception of time's flow is intimately connected to the thermodynamic arrow of time. We remember the past because our brains are physical systems that record information in a way that increases entropy. We can't remember the future because doing so would require our brains to spontaneously decrease in entropy, which is overwhelmingly improbable. The entropy increase also explains why we can influence the future, but not the past. When we make decisions and take actions, we're using the energy in our bodies to create organized, low entropy structures like buildings, artworks, or written words. But this local decrease in entropy is always accompanied by a larger increase in entropy elsewhere, usually in the form of heat dissipated to the environment. Consider what happens when you write a sentence on a piece of paper. You're creating organized, low entropy information. But to do this, your muscles must contract, your neurons must fire, and your metabolism must convert chemical energy into mechanical work. All of these processes generate heat and increase the total entropy of the universe by more than the entropy decrease represented by the organized writing. This principle extends to all forms of information processing and organization. Computers can perform complex calculations and store vast amounts of organized data, but they do so by dissipating heat and increasing the entropy of their environment. The fundamental trade-off between information and entropy is what gives time its direction and makes computation possible. The universality of entropy increase is truly remarkable. It applies to everything from the smallest quantum systems to the largest structures in the universe. Stars burn by converting the organized nuclear fuel in their cores into more randomly distributed energy and matter. Galaxies evolve by gravitational processes that increase entropy. Even black holes, which might seem like perfectly organized objects, actually have enormous entropy proportional to the area of their event horizons. But entropy doesn't just explain why time has a direction, it also explains why that direction is the same everywhere in the observable universe. If different regions of space had different directions for time's arrow, we would see some regions where entropy decreases and others where it increases. Instead, we observe that entropy increases everywhere, creating a universal arrow of time that points in the same direction throughout the cosmos. This universality suggests that the arrow of time we experience isn't just a local phenomenon, but reflects a fundamental property of our universe as a whole. The fact that our entire observable universe started in a low entropy state, the so-called Big Bang, and has been evolving toward higher entropy states ever since, creates the cosmic arrow of time that governs everything from the expansion of space to the formation of stars and planets to the evolution of life itself. The statistical nature of entropy also reveals something profound about the nature of physical law itself. Unlike the deterministic equations of fundamental physics, the second law of thermodynamics is statistical. It doesn't tell us exactly what will happen in every case, but rather what's overwhelmingly likely to happen on average. This statistical nature bridges the gap between the reversible laws of microscopic physics and the irreversible phenomena we observe in the macroscopic world. Understanding entropy as the source of time's arrow also helps us appreciate why the arrow is so robust and universal. It doesn't depend on any particular physical mechanism or force, but rather emerges naturally from the statistical behavior of large numbers of particles. This is why entropy increase appears in every branch of physics, from thermodynamics to information theory to cosmology. Yet even as entropy explains the arrow of time we observe, it raises new questions about the nature of time itself. If entropy increase creates our perception of time's flow, what would happen if entropy somehow began to decrease? Would time appear to flow backward? And if so, would we even notice the change? This brings us to one of the most mind-bending questions in all of physics. Imagine that right now, at this very moment, the direction of time suddenly reversed. Entropy began decreasing instead of increasing. Broken objects started spontaneously repairing themselves. Smoke began flowing back into fires. Your coffee cup started getting hotter instead of cooling down. Would you notice this dramatic change? The answer might surprise you. The short answer is no, you would not notice time reversing. In fact, you couldn't notice it, even in principle. This isn't because the changes would be too subtle to detect, but because your very ability to detect and remember changes depends on the same thermodynamic processes that would be reversing along with everything else. Let's think about what it means to notice something. When you observe an event, light bounces off objects and enters your eyes. Your retina converts this light into electrical signals that travel along your optic nerves to your brain. Your brain processes these signals, compares them with stored memories, and creates the conscious experience of perception. Finally, your brain stores a record of this new experience as a memory for future reference. Every single step in this process involves entropy increase. The photons that carry visual information from objects to your eyes represent energy flowing from organized sources to more random states. The chemical reactions in your retina that convert light into electrical signals generate heat and increase entropy. The electrical impulses traveling along your nerves dissipate energy and create disorder. The formation of new memories in your brain involves complex biochemical processes that all increase the total entropy of your neural system. Now imagine that time reverses and entropy begins decreasing. All of these processes would run backward. Photons would flow from your eyes back to the objects you were looking at. The electrical signals in your retina would convert back into light. The nerve impulses would travel backward from your brain to your sensory organs. Most crucially, your memories would begin disappearing, starting with the most recent ones and working backward through time. But here's the key insight. If your memories are disappearing in reverse chronological order, then your subjective experience of time would still feel like it's moving forward. At any given moment, you would remember everything up to that point in the reverse timeline, and you would have no memory of events that occurred after that point. From your perspective, you would still be experiencing new events and forming new memories in what feels like a forward direction through time. Think of it this way. Imagine watching a movie of someone's life played in reverse. To an outside observer, the person in the movie appears to be getting younger, unlearning things, and experiencing events in backward order. But if you could somehow experience that reversed life from the inside, it would feel completely normal. You would remember your childhood, learn new things as you got older, and experience events in what feels like a natural forward sequence, even though the whole process is actually running backward. This phenomenon isn't just theoretical speculation. It follows necessarily from our understanding of how consciousness and memory work. Your sense of temporal flow isn't based on some mystical perception of time itself, but rather on the accumulation of memories and the experience of forming new ones. If the physical processes underlying memory formation reverse, then your subjective experience of time's direction reverses along with them. Consider what happens when you watch a movie played in reverse. You see people walking backward, water flowing uphill, and broken objects reassembling themselves. These scenes look strange because they violate your expectations based on your forward time experience. But if your brain were also operating in reverse, processing information backward, and losing memories in reverse chronological order, then these reversed scenes would look perfectly normal to you. The same principle applies to all aspects of consciousness and perception. Your ability to think logically depends on neural processes that create associations between ideas and build complex thoughts from simpler components. If these processes reversed, you would still experience logical thinking, but the logic would unfold in the opposite direction. You would start with complex conclusions and work backward to simpler premises. But this would feel like normal forward reasoning to your reversed consciousness. Even your emotional responses would reverse appropriately. If time reversed, you might see a person gradually transition from crying to smiling. To a forward time observer, this would look like someone whose sadness spontaneously transforms into joy for no apparent reason. But to your reversed consciousness, you would perceive a clear emotional narrative unfolding in what feels like a natural forward direction. This extends to learning and understanding as well. In reversed time, you would appear to gradually forget things you once knew, starting with complex skills and working backward to simpler ones. But from your internal perspective, you would experience this as learning and discovery. You would feel like you're gaining new insights and understanding new concepts, even though an outside observer would see you losing knowledge. The implications become even more profound when we consider language and communication. In reverse time, conversations would appear to run backward. People would start with complex statements, break them down into simpler phrases, and end with individual words or sounds. Written text would appear to dissolve, with words disappearing from pages and ink flowing back into pens. But if everyone's consciousness were reversed, these backward conversations and disappearing texts would feel like normal communication. Perhaps most remarkably, your sense of cause and effect would also reverse seamlessly. In forward time, you experience events as having causes that precede their effects. You see a ball thrown before it hits a target, hear thunder after seeing lightning, feel heat before noticing a fire. In reverse time, you would experience effects before their causes, but your reversed memory formation would make this feel completely natural. You would remember the effect occurring, then observe its cause, and this would feel like a normal causal sequence to your reversed consciousness. This principle even applies to your sense of purpose and goal-oriented behavior. In forward time, you form intentions, make plans, and then carry them out. In reverse time, you would appear to start with completed actions and work backward to the original intentions. But your reversed consciousness would experience this as normal goal-directed behavior, forming what feels like intentions and then carrying them out in what seems like the natural forward direction. The reversibility of consciousness also extends to complex cognitive processes like problem-solving and creativity. In forward time, you might struggle with a difficult problem, explore various approaches, and eventually find a solution. In reverse time, this would appear as starting with a solution, gradually forgetting parts of it, and ending up confused about the original problem. But your reversed consciousness would experience this as a natural process of discovery and understanding. Even social interactions would reverse seamlessly from the internal perspective. Relationships would appear to evolve backward, with people gradually becoming strangers after starting as close friends. Conversations would run in reverse, with people starting by saying goodbye and ending by saying hello. But to the reversed consciousness of everyone involved, these interactions would feel like normal relationship development and communication. The physics underlying this remarkable property is rooted in the time symmetry of fundamental laws we discussed earlier. Since the basic equations governing neural activity, chemical reactions, and information processing are all time reversible, there's no fundamental reason why consciousness couldn't operate equally well in either temporal direction. The directional nature of consciousness in our experience comes entirely from the thermodynamic arrow of time, not from any inherent temporal orientation of consciousness itself. This leads to a startling conclusion about the nature of consciousness and time. Your subjective experience of temporal flow might not be detecting the actual direction of time at all, but rather the direction of entropy increase in your brain and environment. If entropy reversed, your consciousness would reverse along with it, and you would have no way to detect the change because your very ability to detect and remember changes would be operating in the new direction. This raises profound questions about the relationship between consciousness and physical time. If consciousness can operate equally well in either temporal direction, then our feeling that time flows might be more of an illusion created by the accumulation of memories than a direct perception of temporal reality. The universe might not have an objective temporal flow at all, just the statistical tendency for entropy to increase in the direction we call future. But this analysis assumes that time reversal would affect everything simultaneously and completely. What if entropy reversed gradually or only partially? What if different systems reversed at different rates? These questions point us toward even deeper mysteries about the nature of time reversal and its relationship to the structure of reality itself. Having established that time reversal is theoretically possible and that we wouldn't notice it if it happened, we now face the ultimate question. Could time actually reverse in our universe? This isn't just a thought experiment anymore. Real physicists have proposed genuine scientific scenarios where the arrow of time might flip, where entropy could begin decreasing, and where the future might become the past. The most dramatic possibility comes from cosmology and our understanding of the universe's ultimate fate. according to current observations, our universe is expanding and cooling, with entropy steadily increasing toward what physicists call heat death. This is a state where all energy is evenly distributed, all processes have stopped, and maximum entropy has been reached. But some cosmological models suggest this might not be the end of the story. One fascinating scenario is the Big Crunch hypothesis. While current evidence suggests our universe will expand forever, some theoretical models propose that the expansion could eventually slow down, stop, and then reverse into a contraction phase. In this scenario, galaxies would begin moving toward each other instead of away, space itself would shrink, and the universe would eventually collapse back into an infinitely dense singularity similar to the Big Bang. During this contraction phase, something remarkable might happen to the arrow of time. Some physicists have proposed that as the universe contracts, the thermodynamic arrow of time could reverse. Instead of entropy increasing toward maximum disorder, it would begin decreasing toward greater organization. Broken objects would spontaneously repair themselves, stars would begin gathering fuel instead of burning it, and all the processes we associate with aging and decay would run in reverse. This isn't just wild speculation. The mathematics of general relativity allows for such scenarios, and the connection between cosmic expansion and thermodynamic time direction has solid theoretical foundations. The idea is that the expansion of space provides the fundamental arena in which entropy can increase. When space contracts, this arena reverses, potentially dragging the thermodynamic arrow along with it. Even more intriguing are cyclic universe models, which suggest that Big Bang and Big Crunch events might repeat endlessly throughout eternity. In these scenarios, our current expanding phase would eventually reverse into a contracting phase, which would end in a Big Crunch, followed by another Big Bang, and so on forever. Each cycle might have its own thermodynamic arrow of time, pointing toward the Big Crunch in each cycle. But the time reversal scenarios don't require waiting for cosmic collapse. Some physicists have explored whether time reversal could occur through quantum mechanical processes. Quantum mechanics, remember, is perfectly time-symmetric at the fundamental level. While macroscopic quantum effects usually increase entropy, there are theoretical scenarios where quantum processes could spontaneously reverse the thermodynamic arrow. One such scenario involves what physicists call quantum tunneling on a cosmic scale. Just as individual particles can tunnel through energy barriers that would be impossible to cross classically, entire macroscopic systems might theoretically tunnel from high entropy states to low entropy states. The probability would be astronomically small, but it wouldn't be zero. Consider our earlier example of gas molecules in a container. We calculated that the probability of all molecules spontaneously clustering on one side is about 1 in 10 to the power of 30. While this is incredibly unlikely, it's not impossible. Now scale this up to cosmic proportions. There's a finite, though unimaginably tiny, probability that all the matter and energy in the observable universe could spontaneously organize itself into a lower entropy configuration. This might sound like pure fantasy, but it has serious implications for our understanding of time and causality. If such quantum tunneling events could occur, even with vanishingly small probability, then time reversal becomes not just theoretically possible, but physically inevitable given enough time. Over truly vast timescales, much longer than the current age of the universe, such improbable events would eventually occur. Another quantum mechanical route to time reversal involves the concept of Poincaré recurrence. This mathematical theorem states that any finite system will eventually return arbitrarily close to its initial state if you wait long enough. Applied to the universe, this suggests that, given enough time, all the particles in the cosmos would eventually return to nearly the same positions and velocities they had at some earlier time. The timescales involved are almost beyond comprehension. For a system with the number of particles in the observable universe, the Poincaré recurrence time would be approximately 10 to the power of 10 to the power of 120 years. This number is so large that writing it out would require more digits than there are atoms in the universe. But the theorem guarantees that such recurrence will eventually occur. During a Poincaré recurrence event, the universe would essentially replay its entire history in reverse, with every process running backward toward the recurrence point. Stars would unexplode, galaxies would disassemble, and eventually the entire cosmos would return to a state resembling the Big Bang. This represents a form of natural time reversal that emerges purely from the deterministic evolution of physical systems. More speculative scenarios for time reversal come from advanced quantum field theory and string theory. Some models suggest that the fundamental structure of space-time itself might be more flexible than we currently understand. In certain exotic conditions, involving extremely high energies or unusual topological configurations, the normal relationship between space and time might break down, potentially allowing for regions where time flows backward relative to the rest of the universe. String theory, in particular, suggests that our familiar three-dimensional space and one-dimensional time might be projections of a higher dimensional reality with a much richer structure. In this higher dimensional space, relationships between space and time could be far more complex than we observe. Time-like and space-like directions might be interchangeable under certain conditions, opening up possibilities for time reversal that don't exist in our everyday four-dimensional space-time. Another fascinating possibility comes from the study of black holes and their relationship to thermodynamics. Black holes have entropy proportional to the area of their event horizons, and they emit Hawking radiation that carries away energy and information. As a black hole evaporates through Hawking radiation, its entropy actually decreases, representing a form of natural entropy reversal. Some physicists have speculated that under extreme conditions, processes similar to black hole evaporation might occur on larger scales. If the vacuum of space itself could undergo a phase transition, it might be possible for large regions of the universe to spontaneously emit matter and energy while decreasing in entropy. Such regions would effectively experience reversed thermodynamic time. Even more exotic scenarios involve the possibility of closed time-like curves, solutions to Einstein's field equations that allow for paths through space-time that loop back to their starting point in time. While most physicists believe that such curves are prevented by unknown physical principles, their mathematical possibility in general relativity suggests that the structure of time itself might be more malleable than our everyday experience suggests. Quantum mechanics also provides potential mechanisms for time reversal through the phenomenon of quantum measurement and wave function collapse. Some interpretations of quantum mechanics suggest that the act of measurement plays a fundamental role in determining the direction of time's arrow. In these models, different measurement procedures or different conscious observers might experience different directions of temporal flow. The many worlds interpretation of quantum mechanics opens up even more radical possibilities. In this model, every quantum measurement causes the universe to split into multiple parallel realities, each corresponding to a different measurement outcome. Some physicists have speculated that different branches of the multiverse might have different directions for time's arrow, with some branches experiencing forward time, while others experience reverse time. These scenarios also connect to deep questions about the nature of information and computation in physics. If the universe can be viewed as a vast information processing system, then time reversal might be understood as a form of cosmic computation running in reverse. Just as a computer can run a program backward to undo its effects, the universe might be capable of reversing its own computational processes under certain extreme conditions. While all of these scenarios remain highly speculative, they demonstrate that time reversal is not just a philosophical curiosity. but a genuine scientific possibility that emerges from our best current theories of physics. Whether any of these mechanisms could actually operate in our universe remains an open question, but the mathematical frameworks that describe reality contain the seeds of temporal reversal. The exploration of these possibilities has also led to new insights about the relationship between time, information, and consciousness. If time can reverse under certain conditions, then our understanding of causality, free will, and the nature of existence itself might need to be fundamentally revised. The universe might be far stranger and more temporally complex than our forward time experience suggests. Before we delve deeper into the scientific study of time reversal, we need to clear up some fundamental misconceptions that have been popularized by science fiction and misunderstandings of physics. When physicists talk about time reversal, they're not describing the dramatic scenarios you might see in movies or read about in novels. True time reversal, as understood by science, is far more subtle and far more strange than popular culture suggests. First and most importantly, time reversal does not mean that you would consciously experience moving backward through your life. This is perhaps the most common misconception about time reversal. In movies, we often see characters aging in reverse, unlearning things they once knew, or experiencing events in backward order while maintaining their forward time consciousness. This scenario is physically impossible and fundamentally misunderstands how consciousness and memory work. As we explored earlier, consciousness itself is a thermodynamic process that depends on entropy increase. If time reversed, your consciousness would reverse along with it. You would not maintain your current memories while watching the world run backward around you. Instead, your memories would disappear in reverse chronological order, and your subjective experience would continue to feel like forward time progression. You would never experience the disorienting sensation of watching your life unfold in reverse, because your very ability to experience and remember would be running backward as well. This means that the dramatic possibilities explored in science fiction, where conscious beings retain their forward time memories while experiencing a backward time world, are not just unlikely, but impossible according to our understanding of physics and neuroscience. Consciousness is not separate from the physical processes it emerges from, and those processes are subject to the same thermodynamic laws that govern everything else. Another major misconception is that time reversal would allow for paradoxes or violations of causality. In popular depictions, time reversal often leads to grandfather paradox type situations, where effects occur before their causes, or where people can change the past in ways that contradict their present circumstances. But true time reversal, as understood by physics, maintains perfect consistency between cause and effect. In reverse time, causes would still precede effects within the reverse temporal framework. What we call the future in forward time would become the causal past in reverse time, and what we call the past would become the causal future. But the causal relationships themselves would remain intact and consistent. Every effect would still have an appropriate cause, and every cause would still produce its proper effect, just in the opposite temporal direction from our current perspective. This means that time reversal could never be used to change the past or alter history. If time reversed starting from this moment, the entire future history of the universe would be completely determined by the requirement that it must lead, in reverse, to all the events that have already occurred. There would be no room for free will or choice in a time-reversed universe, just as there is no room to change the past in our current forward time universe. Time reversal also does not mean that individual objects or people would age in reverse while everything else continues normally. This scenario, popular in fiction, violates the fundamental principle that time reversal must affect all thermodynamic processes simultaneously. You cannot have some entropy increasing processes and some entropy decreasing processes occurring in the same region of spacetime, because entropy is a property of entire systems, not individual objects. If a person was somehow aging in reverse while surrounded by a forward time environment, the thermodynamic inconsistencies would be enormous. Their body would need to expel organized energy while absorbing random heat. Their brain would need to erase memories while the environment continued to provide new sensory input, and their metabolism would need to run backward while consuming forward time food and oxygen. These processes are thermodynamically impossible without reversing the entire environment as well. Similarly, time reversal does not mean that gravity would push instead of pull, or that electromagnetic forces would repel instead of attract. The fundamental forces of nature are already time-symmetric in their mathematical descriptions. If time reversed, gravity would still be attractive, electromagnetic forces would still follow Maxwell's equations, and nuclear forces would still bind atomic nuclei together. The forces themselves would not change direction or character. What would change is the statistical behavior of large collections of particles governed by these forces. Instead of gravitational collapse leading to increased entropy through heating and radiation, reverse time would see gravitational expansion leading to decreased entropy through cooling and energy absorption, but the force of gravity itself would remain attractive throughout. Another important clarification is that time reversal does not violate conservation laws. Energy, momentum, angular momentum, and electric charge would all remain conserved in a time-reversed universe. These conservation laws emerge from fundamental symmetries of nature that are maintained under time reversal. What changes is not the total amount of conserved quantities, but the direction in which they flow and transform. In forward time, we see organized energy sources like nuclear fuel gradually converting to disorganized thermal energy and radiation. In reverse time, we would see disorganized thermal energy spontaneously organizing itself into concentrated energy sources. But the total energy content would remain constant throughout, satisfying conservation of energy perfectly. Time reversal also does not create energy or matter from nothing. Every particle that appears in reverse time processes would be exactly balanced by particles that disappear. Every bit of energy that becomes organized would be exactly balanced by energy that becomes disorganized elsewhere in the system. The universe would not gain or lose anything. It would simply redistribute its existing content in the opposite direction from what we normally observe. Perhaps most importantly, time reversal does not provide a mechanism for faster-than-light travel or communication. While reverse time processes might appear to propagate information backward through time, this information would not be accessible to forward time observers. The apparent backward information flow would be entirely consistent with the causal structure of space-time and would not allow for any violations of relativity. The misconception that time reversal could enable time travel in the science fiction sense of moving between different time periods is also fundamentally incorrect. Time reversal affects the direction of thermodynamic processes throughout the universe, but it does not transport objects or information between different temporal locations. A time-reversed universe would still evolve continuously through space-time, just in the opposite direction from our current experience. Time reversal also does not mean that the laws of physics themselves would change or operate differently. The same equations that govern forward time evolution would continue to govern reversed time evolution. Newton's laws, Maxwell's equations, the Schrödinger equation, and Einstein's field equations would all remain valid and unchanged. What would reverse is not the laws themselves, but the direction in which physical systems evolve under those laws. Another crucial point is that time reversal does not create determinism where none existed before, nor does it eliminate quantum uncertainty. Quantum mechanical processes would continue to be probabilistic in reverse time with the same fundamental uncertainties and measurement relationships. The direction of time reversal affects the direction of entropy flow, but it does not change the intrinsically probabilistic nature of quantum events. Finally, time reversal does not solve the problem of the beginning or end of time. A time-reversed universe would still have the same temporal boundaries as a forward time universe, just experienced in the opposite direction. If our universe began with a Big Bang and will end in heat death, a time-reversed universe would begin with heat death and end with a Big Bang. The fundamental questions about what happens at the temporal boundaries of existence remain unchanged. Understanding what time reversal is not helps us appreciate what it actually is: a profound reorganization of thermodynamic processes that maintains all the fundamental laws and symmetries of physics, while creating a universe that evolves toward greater organization instead of greater disorder. This understanding sets the stage for examining how scientists actually study and test these ideas in controlled laboratory conditions. The distinction between scientific time reversal and popular misconceptions is crucial for understanding the real implications of these ideas for our comprehension of time, causality, and the nature of reality itself. Only by clearing away the fictional elements can we appreciate the genuine strangeness and profound implications of what time reversal might actually mean for our universe. While time reversal on cosmic scales remains theoretical, scientists have been conducting real experiments that demonstrate time reversal phenomena in controlled laboratory conditions. These studies don't involve reversing time for entire universes, but they do show that the fundamental time symmetry of physics can be observed and manipulated in carefully designed systems. The results provide crucial insights into the nature of time and validate our theoretical understanding of temporal symmetry. One of the most important areas of time reversal research occurs in particle physics laboratories around the world. At facilities like CERN in Switzerland, Fermilab in the United States, and Keck in Japan, physicists routinely test the fundamental symmetries of nature, including time reversal symmetry. These experiments probe the deepest levels of reality, examining whether the basic laws governing subatomic particles truly treat forward and backward time equally. The most precise tests involve studying what physicists call CPT symmetry, which combines charge conjugation, parity reversal, and time reversal. According to fundamental principles of quantum field theory, if you simultaneously reverse the charge of all particles, flip the spatial coordinates, and reverse the direction of time, the laws of physics should remain exactly the same. This CPT theorem is one of the most fundamental principles in all of physics. Researchers test this symmetry by comparing the properties of particles and antiparticles with extraordinary precision. They measure the masses, lifetimes, and decay patterns of particles like kaons and b-mesons, then compare these with the corresponding properties of their antiparticles. Any difference would indicate a violation of CPT symmetry and suggest that time reversal might not be a perfect symmetry of nature. So far, these experiments have confirmed CPT symmetry to incredible precision. The masses of particles and antiparticles agree to better than 1 part in 10 to the 18th power. The lifetimes match to similar precision. These results strongly support the idea that time reversal is indeed a fundamental symmetry of the microscopic world, even if we don't observe it in macroscopic systems. But some of the most dramatic demonstrations of time reversal occur in quantum mechanical systems, where scientists can actually observe processes running backward in time. These quantum time reversal experiments don't violate thermodynamics because they involve isolated systems with very few particles, where statistical effects that normally enforce the arrow of time become negligible. One remarkable example is the phenomenon of quantum revival, where quantum wave functions spontaneously return to their earlier states. In these experiments, scientists prepare atoms or molecules in specific quantum states, allow them to evolve and become complex and disordered, and then observe them spontaneously returning to their original simple states. This represents genuine time reversal at the quantum level. Consider an experiment with a hydrogen atom placed in a strong magnetic field. Scientists can prepare the electron in a simple quantum state, Then watch as quantum evolution spreads the wave function over many different energy levels, creating a complex superposition. The system becomes increasingly disordered from a quantum perspective. But then, after a specific time period called the revival time, the wave function spontaneously reassembles itself into the original simple state. This revival process looks exactly like time reversal. The electron appears to retrace its quantum evolution backward, undoing all the complexity that had developed. The process is completely deterministic and can be predicted precisely using the Schrödinger equation. It demonstrates that time reversal is not just theoretically possible, but actually observable in real physical systems under the right conditions. Even more striking are experiments where scientists actively induce time reversal in quantum systems. Using carefully timed electromagnetic pulses, researchers can effectively reverse the quantum evolution of atoms and molecules, forcing them to retrace their quantum paths backward through time. These experiments represent some of the most direct demonstrations of time reversal ever achieved in laboratory settings. One particularly elegant example involves nuclear magnetic resonance, the same technology used in medical MRI scanners. In these experiments, scientists prepare nuclear spins in organized states, allow them to evolve into disordered configurations, and then apply precise pulse sequences that reverse the evolution. The spins retrace their paths exactly, returning to their original organized states with remarkable fidelity. These NMR time reversal experiments can involve thousands of nuclear spins, making them among the largest scale quantum time reversal demonstrations ever performed. The fact that such complex many-body systems can be made to evolve backward in time provides strong evidence for the time symmetry of quantum mechanics and shows that time reversal remains possible even in relatively large quantum systems. Scientists have also achieved time reversal in optical systems, manipulating light waves to propagate backward through complex media. Using techniques called optical phase conjugation, researchers can create light beams that retrace their paths through distorting materials, automatically correcting for all the distortions they encountered on their forward journey. These systems demonstrate time reversal symmetry in electromagnetic fields and have practical applications in laser technology and optical communications. Perhaps the most philosophically intriguing experiments involve tests of quantum mechanical retrocausality, the idea that quantum measurements might influence past events. While these experiments don't demonstrate macroscopic time reversal, they probe whether quantum mechanics allows for subtle forms of backward time influence that don't violate causality. The delayed choice quantum eraser experiments represent some of the most sophisticated tests of these ideas. In these studies, scientists perform quantum interference experiments where the decision about which measurement to perform is made after the quantum particles have already passed through the experimental apparatus. Remarkably, the results suggest that the later measurement decision affects the earlier quantum behavior, as if information about the future measurement somehow propagates backward in time. While these results don't violate causality or allow for faster than light communication, they do suggest that quantum mechanics might involve subtle time-symmetric correlations that challenge our classical notions of temporal order. The particles don't receive information from the future, but their quantum states seem to reflect the measurement choices that will be made later. Researchers have also demonstrated time reversal in thermodynamic systems, though only on very small scales where statistical fluctuations can temporarily overcome the second law of thermodynamics. Using optical tweezers to manipulate individual particles in solution, scientists have observed and controlled violations of the second law, watching entropy decrease in tiny systems for brief periods. In these experiments, researchers trap single colloidal particles in laser beams and monitor their random thermal motion. Occasionally, purely by chance, the particles move in ways that decrease the entropy of the system. Scientists can enhance these fluctuations using feedback control, creating situations where small systems consistently violate the second law and evolve toward more organized states. While these violations only last for short times and involve tiny amounts of energy, they demonstrate that the statistical nature of the second law allows for temporary time reversal, even in thermodynamic systems. The experiments provide direct evidence that entropy decrease and apparent time reversal are possible, albeit rare, even in classical systems. Advanced laser cooling experiments have achieved even more dramatic temporary violations of thermodynamics. By using precisely controlled laser pulses, scientists can remove thermal energy from atomic gases so efficiently that the atoms briefly evolve toward more organized states. The gases spontaneously form ordered structures and exhibit reduced entropy for short periods before thermal fluctuations restore normal thermodynamic behavior. Computer simulations have also provided crucial insights into time reversal phenomena. Using powerful supercomputers, researchers can simulate the evolution of complex systems both forward and backward in time, testing theoretical predictions about time symmetry and entropy. These simulations have revealed surprising details about how time reversal might manifest in different physical systems. One particularly important class of simulations involves molecular dynamics, where scientists track the motion of thousands or millions of atoms as they interact according to fundamental physical laws. By recording the positions and velocities of all atoms at a particular time, then reversing all the velocities, researchers can make the entire system evolve backward in time. These simulations confirm that microscopic time reversal is possible and reveal how quickly thermodynamic irreversibility emerges in many particle systems. The experimental study of time reversal has also led to practical technologies. Time reversal techniques are now used in medical ultrasound to focus acoustic waves with unprecedented precision, in seismology to track earthquake sources, and in underwater acoustics for submarine detection. These applications demonstrate that time reversal symmetry is not just a theoretical curiosity, but a useful principle for solving real-world problems. Looking toward the future, scientists are planning even more ambitious time reversal experiments. Proposals include creating macroscopic quantum superpositions that could be made to evolve backward in time, using advanced laser cooling to achieve large-scale entropy reduction, and employing quantum computers to simulate time-reversed evolution of complex systems with perfect fidelity. These experimental investigations of time reversal provide crucial evidence for our theoretical understanding of time symmetry, while revealing the practical limits and possibilities for temporal manipulation. They show that while macroscopic time reversal remains beyond our current capabilities, the fundamental time symmetry of physics is real and observable under the right conditions. Given that time reversal symmetry is fundamental to physics, and given that we've demonstrated time reversal in laboratory experiments, a profound question emerges. If the universe could just as easily evolve backward in time as forward, why do we only observe forward time evolution? Why don't we see regions of space where entropy decreases, where broken objects spontaneously repair themselves, where smoke flows back into fires? The answer to this puzzle takes us to the very heart of cosmology and our understanding of the universe's origin. The key insight comes from recognizing that the arrow of time we observe isn't a fundamental feature of physical law, but rather a consequence of the initial conditions of our universe. The Big Bang, the event that began our cosmic history 13.8 billion years ago, established a state of extremely low entropy that has been increasing ever since. This initial low entropy state is what creates the arrow of time we experience throughout the observable universe. To understand why this matters, imagine our universe as a vast cosmic egg that was perfectly organized at the moment of the Big Bang. This organized state represented minimum entropy for the early universe. Ever since then, this cosmic egg has been breaking, spreading its contents throughout space and increasing entropy in the process. We observe forward time evolution because we're witnessing the ongoing process of cosmic entropy increase that began with the Big Bang. But here's the crucial point. There's nothing in the fundamental laws of physics that required the universe to begin in a low entropy state. The Big Bang could, in principle, have started with maximum entropy instead of minimum entropy. If it had, the universe would have evolved toward decreasing entropy, and we would observe what appears to be backward time evolution. Broken eggs would spontaneously reassemble, stars would gather fuel instead of burning it, and all processes would run in reverse compared to what we actually observe. The fact that our universe began with low entropy rather than high entropy is what physicists call a boundary condition, not a fundamental law. It's similar to how a ball could roll either uphill or downhill depending on where you place it initially, even though gravity always pulls downward. The laws of physics allow for both possibilities, but the initial conditions determine which one actually occurs. This boundary condition explanation has profound implications for our understanding of time and causality. It suggests that the arrow of time is not built into the fabric of reality itself, but emerges from the particular way our universe happened to begin. In a multiverse scenario, where many universes exist with different initial conditions, some would have forward time arrows like ours, while others would have backward time arrows. But this raises an even deeper question. Why did our universe begin in such a special, low entropy state? This is one of the greatest unsolved problems in cosmology. The probability of the universe spontaneously beginning in such an organized configuration is astronomically small, yet this is exactly what appears to have happened. Some physicists call this the past hypothesis problem, the mystery of why the past was so special compared to what we would expect from random initial conditions. Several theoretical solutions have been proposed. One possibility is that the low entropy beginning wasn't actually random, but was necessary for some deeper reason we don't yet understand. Perhaps the laws of physics or the nature of quantum gravity require universes to begin in low entropy states. Another possibility is that our universe is just one of countless universes in a multiverse, and we observe a low entropy beginning because only such universes can develop the complexity necessary for observers like us to exist. The inflation theory of cosmology provides another perspective on this puzzle. According to this model, the very early universe underwent a period of exponential expansion that stretched space to enormous scales and left it in a remarkably smooth, low entropy state. The inflationary process might naturally produce low entropy initial conditions, explaining why our universe began the way it did without requiring special fine-tuning. But even if inflation explains the low entropy beginning of our universe, it doesn't explain why we don't observe reverse time regions elsewhere in the cosmos. If space is infinite and contains regions with all possible initial conditions, surely some regions should have started with high entropy and evolved backward in time. Why don't we see evidence of such regions in our astronomical observations? The answer relates to the fundamental problem of observing reverse time systems from a forward time perspective. Remember that observation itself is a thermodynamic process that increases entropy. When we look at distant galaxies through telescopes, we're using photons that carry energy from those galaxies to our detectors. This energy flow represents entropy increase and is fundamentally tied to our forward time perspective. If a region of space were evolving with decreasing entropy, the thermodynamic processes that allow us to observe it would be incompatible with our forward time observation methods. Instead of emitting photons that travel to our telescopes, such a region would be absorbing photons from the cosmic background. Instead of radiating energy outward, it would be concentrating energy inward. These processes would make the region effectively invisible to our forward time observation techniques. Think of it this way. In our forward time universe, stars shine by converting organized nuclear fuel into disorganized radiation that spreads throughout space. This radiation eventually reaches our telescopes, allowing us to observe the stars. But in a reverse time region, the process would run backward. Disorganized radiation would spontaneously organize itself and flow into stars, which would use this energy to create organized nuclear fuel. No radiation would escape for us to observe. This observational limitation means that even if reverse time regions exist elsewhere in the universe, they would be fundamentally undetectable using our forward time observation methods. They would represent a kind of temporal shadow, invisible to us not because they don't emit light, but because they emit light in a way that's incompatible with our entropy-increasing observation processes. The situation becomes even more complex when we consider the relationship between observers and the systems they observe. In our forward time universe, observers like us exist because increasing entropy allows for the complex information processing that consciousness requires. Our brains work by using metabolic energy to create organized neural patterns, a process that increases the entropy of our environment while temporarily decreasing the entropy of our neural systems. But observers in a reverse time region would need to operate on decreasing entropy principles. Their consciousness would need to function by organizing environmental energy while decreasing their own internal organization. Such observers might be fundamentally incompatible with forward time physical processes, making communication or interaction between forward time and reverse time regions impossible, even if both exist. This incompatibility extends to the very concept of information and measurement. In forward time, measurement involves creating records, storing information, and building up databases of knowledge about the world. These are all entropy-increasing processes. In reverse time, measurement would involve erasing records, forgetting information, and breaking down databases. The two types of measurement processes might be mutually exclusive, preventing any exchange of information between forward and reverse time regions. The cosmological principle, which states that the universe is roughly the same everywhere on large scales, also suggests why we don't observe reverse time regions. If the entire observable universe began with the same low entropy Big Bang event, then every region would have the same initial conditions and the same thermodynamic arrow. There would be no reason for different regions to evolve in different temporal directions. However, this uniformity might not extend beyond our observable universe. In an infinite cosmos, regions that are causally disconnected from our Big Bang event might have different initial conditions and different arrows of time. Such regions would be forever beyond our observational reach, separated from us not just by vast distances, but by fundamentally incompatible temporal orientations. The question of reverse time regions also connects to deep issues in the philosophy of time and consciousness. If reverse time regions exist but are unobservable, do they represent real alternative temporal realities? Or are they merely mathematical possibilities that have no physical significance? This question touches on fundamental issues about the relationship between mathematics, physics, and reality itself. Some physicists have proposed that the absence of observable reverse time regions provides evidence for specific cosmological models. If the universe were truly infinite and contained all possible initial conditions, we might expect to observe evidence of reverse time evolution somewhere. The fact that we don't might constrain theories about the size, age, and structure of the cosmos. Advanced theoretical models suggest even more exotic possibilities. In some versions of string theory and quantum gravity, the relationship between space and time becomes more flexible at extremely small scales or high energies. Under such conditions, the distinction between forward and reverse time might break down entirely, leading to regions where temporal orientation becomes undefined or fluctuates randomly. The search for reverse time phenomena has also motivated searches for anomalous astronomical objects that might represent violations of the thermodynamic arrow. These include objects that appear to be emitting organized energy, regions where entropy seems to be decreasing, or systems that show other signs of reverse thermodynamic evolution. So far, no convincing examples have been found, but the search continues as our observational capabilities improve. Understanding why we don't observe reverse time regions ultimately leads us back to the fundamental mystery of time's arrow. The universe's temporal orientation appears to be a global property, established by the initial conditions of the Big Bang and maintained throughout the subsequent cosmic evolution. This global nature of time's arrow might be one of the most fundamental features of our reality, shaping everything from the formation of galaxies to the emergence of life and consciousness itself. One of the most fascinating questions about time reversal concerns whether life could exist in a universe where entropy decreases instead of increases. This isn't just an academic curiosity, it goes to the heart of what life actually is and how biological processes relate to the fundamental laws of thermodynamics. The answer reveals profound connections between the arrow of time, the nature of complexity, and the very possibility of existence as we understand it. To approach this question, we first need to understand what life fundamentally requires from a thermodynamic perspective. All living organisms, from the simplest bacteria to the most complex mammals, are essentially sophisticated machines for processing energy and information. They take in organized energy from their environment, use it to maintain and reproduce their complex internal structures, and expel disorganized waste heat back to the environment. This process invariably increases the total entropy of the universe, even while temporarily decreasing entropy within the organism itself. Consider the basic process of metabolism, which is fundamental to all life as we know it. When you eat food, your digestive system breaks down complex organic molecules into simpler components. Your cells then use these molecules in carefully controlled chemical reactions that extract energy and use it to power cellular processes. The waste products, including carbon dioxide, water, and heat, represent more disorganized forms of the original food molecules. The total entropy of the system increases, even though your body has used some of the energy to maintain its highly organized biological structures. This same principle applies to every biological process. When you grow, your cells divide and create new organized tissue from simpler molecular building blocks. When you think, your neurons fire in complex patterns that process and store information. When you move, your muscles contract in coordinated ways that produce directed motion. All of these processes require energy input and produce entropy increase in the surrounding environment. Now imagine what would happen if time reversed and entropy began decreasing instead of increasing. In such a universe, the thermodynamic processes that power life would need to run backward. Instead of breaking down food molecules to extract energy, organisms would need to spontaneously assemble complex food molecules from simple waste products. Instead of exhaling carbon dioxide and water vapor, they would need to absorb these molecules from the air and use them to construct organized nutrients. The implications become even more striking when we consider biological growth and development. In our forward time universe, organisms start as simple structures and gradually develop into more complex forms. A human begins as a single fertilized cell and develops through precisely orchestrated processes into a complex multicellular organism with specialized organs and systems. This development represents a local decrease in entropy within the organism, powered by a larger increase in entropy in the environment through metabolic processes. In a reverse time universe, this developmental process would need to run backward. Organisms would start as complex, highly differentiated structures and gradually simplify into less organized forms. a reverse-time human would begin as an adult with fully developed organs and systems, then gradually lose complexity until eventually becoming a single undifferentiated cell. The energy to power this reverse development would need to come from organizing environmental disorder rather than breaking down environmental order. But here's where the analysis becomes truly mind-bending. If reverse-time organisms existed, they wouldn't experience this process as reverse development at all. From their internal perspective, with their entropy decreasing consciousness, they would still experience what feels like normal growth and development. They would perceive themselves as starting simple and becoming more complex, just as we do, even though an external forward-time observer would see them doing the opposite. This raises profound questions about what we mean by complexity and organization in biological systems. In our universe, we associate biological complexity with health, vitality, and successful adaptation to environmental challenges. A healthy adult human represents the peak of developmental complexity for our species. But in a reverse-time universe, the equivalent peak might correspond to what we would recognize as the simplest possible biological state. The relationship between life and information processing becomes equally complex in a reverse-time scenario. In our universe, living organisms constantly gather information about their environment, process this information to make survival decisions, and store useful information for future reference. Learning, memory formation, and adaptive behavior are all fundamentally information processing activities that increase entropy through the physical mechanisms that implement them. Reverse-time life would need to operate on opposite information processing principles. Instead of gathering and storing information, organisms would need to be constantly forgetting and losing information about their environment. Instead of learning from experience, they would need to gradually unlearn previously acquired knowledge. Instead of adapting to environmental changes, they would need to become progressively less adapted to their surroundings. Yet from the internal perspective of reverse-time organisms, these processes would still feel like normal learning, memory formation, and adaptation. A reverse-time creature would experience what feels like gaining knowledge and becoming better adapted to its environment, even though the underlying physical processes would be running in the entropy decreasing direction. The question of reproduction in reverse-time life presents particularly intriguing challenges. In our universe, organisms reproduce by using energy and resources to create offspring that carry genetic information into the future. Parents invest organized energy to produce children who can continue the species' lineage. This process increases total entropy while propagating organized genetic information through time. Reverse-time reproduction would need to work differently. Instead of parents creating offspring, the process would need to involve offspring somehow creating parents, or perhaps multiple organisms spontaneously merging into fewer, more organized forms. The genetic information flow would run backward, with future generations somehow providing information to past generations rather than receiving it. But again, from the internal perspective of reverse-time organisms, this backward reproduction would feel like normal forward reproduction. Reverse-time parents would experience what feels like creating and nurturing offspring, even though the underlying thermodynamic processes would be entropy decreasing rather than entropy increasing. The evolution of species in reverse time presents equally fascinating puzzles. In our universe, evolution works through random genetic mutations and natural selection, processes that explore new organizational possibilities and gradually optimize organisms for survival in their environments. This evolutionary process is fundamentally driven by entropy increasing mechanisms, even though it can produce increasingly complex and organized life forms. Reverse-time evolution would need to operate through entropy decreasing mechanisms. Instead of random mutations creating new genetic variations, the process would need to involve spontaneous genetic organization that reduces the variety of possible forms. Instead of natural selection favoring the most adapted organisms, the process would favor the least adapted, gradually reducing the optimization of species for their environments. Yet, reverse time organisms would still experience what feels like evolutionary progress and adaptation. They would perceive their species as becoming better adapted over time, developing new capabilities and exploring new ecological niches, even though the underlying thermodynamic processes would be moving toward less organization and adaptation. The relationship between reverse time life and its environment raises additional complications. In our universe, ecosystems are complex networks of energy and material flows that connect different organisms and environmental components. These ecological relationships are fundamentally based on entropy-increasing processes like predation, decomposition, and nutrient cycling. A reverse-time ecosystem would need to operate on entropy-decreasing principles. Instead of predators hunting prey, the relationship would need to somehow run backward, with prey spontaneously becoming predators or energy flowing from predators back to prey. Instead of decomposition breaking down dead organisms into simpler compounds, the process would need to involve spontaneous assembly of complex organisms from simple environmental chemicals. The very concept of death becomes problematic in reverse time scenarios. In our universe, death represents the ultimate entropy increase for biological systems, the breakdown of organized biological structures into simpler chemical components. In reverse time, death would need to represent entropy decrease, the spontaneous assembly of organized biological structures from simpler components. What we call birth and death would essentially exchange roles. These considerations suggest that life as we understand it, based on metabolism, growth, reproduction, and adaptation through entropy-increasing processes, could not exist in a reverse-time universe. The fundamental thermodynamic requirements for biological processes would be incompatible with decreasing entropy. However, this doesn't necessarily mean that no form of organized, complex, possibly even conscious entities could exist in reverse time. There might be entirely different organizing principles that could operate in entropy-decreasing environments, creating forms of complexity and organization that have no analogy in our forward time experience. Such reverse time complexity might be based on entirely different physical and chemical processes than the ones that support life in our universe. Instead of relying on controlled chemical reactions that extract energy from environmental sources, reverse time complexity might be based on processes that spontaneously organize environmental energy into concentrated forms. The possibility of reverse time consciousness is particularly intriguing. If consciousness can emerge from sufficiently complex information processing systems, and if reverse time systems could achieve equivalent complexity through entropy-decreasing processes, then reverse time consciousness might be possible, even if it operates on completely different principles than our entropy-increasing consciousness. But any such reverse time consciousness would be fundamentally alien to our understanding. It would process information, form memories, and make decisions through mechanisms that have no parallel in our experience. Communication or interaction between forward time and reverse time conscious entities might be impossible, not just practically, but in principle, due to the incompatible thermodynamic foundations of their cognitive processes. Ultimately, the question of whether life could exist in reverse time reveals the deep connections between biology, thermodynamics, and the nature of time itself. Life as we know it appears to be fundamentally dependent on the arrow of time we observe, suggesting that the direction of entropy increase isn't just a cosmic accident, but a necessary condition for the emergence of the complexity and organization that makes existence possible. As we near the end of our exploration of time reversal, we must grapple with the deepest questions about what time's direction actually means for our understanding of reality. The discoveries we've made along this journey, from fundamental time symmetry to entropy's arrow, from quantum time reversal to cosmic evolution, paint a picture of time that is far stranger and more subtle than our everyday experience suggests. The direction of time might not be what we think it is at all. Throughout most of human history, time's forward flow seemed as fundamental and unchangeable as the existence of space itself. We age, we remember the past, but not the future. We see cause followed by effect, and we watch the universe evolve from organized states to disorganized ones. This directional flow feels so basic to our experience that questioning it seems almost absurd. Yet physics has revealed that this apparent flow might be more of an emergent illusion than a fundamental feature of reality. The key insight comes from recognizing that the fundamental laws of physics make no distinction between past and future. Newton's equations, Maxwell's laws of electromagnetism, the Schrödinger equation of quantum mechanics, and Einstein's field equations of general relativity all treat time as a simple coordinate. Much like the three dimensions of space, these equations work equally well whether time increases or decreases, whether we call a particular direction past or future. This time symmetry suggests that at the deepest level, the universe might not have an intrinsic temporal orientation at all. Instead of time flowing like a river from past to future, reality might be more like a static four-dimensional landscape, where all events, past and future, exist simultaneously. Our perception of temporal flow might arise not from time actually moving, but from the way our consciousness navigates through this static temporal landscape. Consider an analogy that helps illustrate this perspective. Imagine you're driving along a mountain road that winds through a valley. From your perspective in the car, you're moving through a sequence of changing scenes, first seeing mountains ahead, then valleys to the side, then forests behind you. The landscape seems to flow past you in a directed sequence. But from an aerial view, the entire landscape exists simultaneously. Your sense of directional flow comes not from the landscape moving, but from your movement through a static geographic space. Time might work similarly. All events throughout the history and future of the universe might exist simultaneously in what physicists call the block universe or eternalism model. Your consciousness moves through this temporal landscape, creating the subjective experience of flowing time. But the landscape itself is static and eternal. Past events don't cease to exist when they're behind you, and future events already exist even though you haven't reached them yet. This perspective helps explain why the fundamental equations of physics are time symmetric. If all times exist equally, then there's no fundamental reason to prefer forward over backward temporal directions. The equations describe relationships between events at different times, but they don't require any particular direction of temporal navigation through those relationships. But this raises a profound puzzle. If the block universe model is correct, and if all times exist equally, then why do we experience such a strong sense of temporal flow in one particular direction? Why doesn't our consciousness move randomly through time, sometimes forward and sometimes backward, like a car that sometimes drives forward and sometimes in reverse along the mountain road? The answer brings us back to entropy and thermodynamics, but with a deeper understanding of their role. Entropy doesn't create time's flow, but rather creates the conditions that allow consciousness to develop and operate in a particular temporal direction. Consciousness requires complex information processing systems, and such systems can only exist and function in regions of space-time where entropy increases in a consistent direction. Think of entropy increase as creating a kind of temporal terrain that consciousness can navigate. Just as a car needs roads to drive on, consciousness needs the thermodynamic infrastructure created by increasing entropy to support the complex processes of memory formation, information processing, and decision-making. Without this infrastructure, consciousness cannot exist, let alone move through time. This perspective suggests that consciousness and entropy increase are intimately connected, not because consciousness creates the arrow of time, but because the arrow of time creates the conditions necessary for consciousness. We experience forward temporal flow because we are entropy-increasing information processing systems embedded in an entropy-increasing region of space-time. But this connection between consciousness and entropy raises even deeper questions about the nature of subjective experience. If consciousness requires entropy increase to function, then conscious observers can only exist in regions of space-time where thermodynamic time arrows point in consistent directions. This might explain why all conscious observers in our region of the universe experience the same temporal direction, and why we don't encounter conscious beings with opposite temporal orientations. The implications extend to free will and causality as well. In a block universe where all events exist simultaneously, the traditional notion of free will becomes problematic. How can we make free choices about the future if the future already exists as definitively as the past? How can our decisions cause future events if those events are already embedded in the eternal temporal landscape? One possible resolution involves recognizing that causality itself might be an emergent property of entropy increase rather than a fundamental feature of time. In the block universe, events are correlated with each other in complex patterns. But these correlations don't necessarily imply that earlier events cause later events. Instead, our perception of causality might arise from the way our entropy-increasing consciousness processes information about these correlations. From this perspective, we experience ourselves as making free choices and causing future events because our information processing systems naturally interpret temporal correlations in causal terms. The feeling of making a decision and seeing its consequences unfold is real as a subjective experience, even if the underlying reality involves static correlations in the block universe rather than dynamic causal influences. This interpretation also provides a new perspective on the meaning of scientific prediction and explanation. When physicists use equations to predict future events from past conditions, they're not necessarily describing how past events cause future events, but rather mapping the correlational structure that exists throughout the block universe. The equations work because they describe real relationships between different regions of spacetime, regardless of whether we interpret these relationships in causal terms. The relationship between time's direction and information becomes particularly profound from this perspective. Information, in the technical sense used by physicists, is always associated with organization and structure. Creating, processing, and storing information requires entropy-increasing processes. This suggests that information itself might have a natural temporal orientation tied to the thermodynamic arrow. In our universe, information flows from past to future because information processing requires entropy increase, and entropy increases toward what we call the future. But in a hypothetical reverse time region, information would flow from what we call future to past, because the thermodynamic arrow would point in the opposite direction. The direction of information flow defines the direction of temporal experience for any conscious observer. This connection between information and temporality also illuminates the relationship between knowledge and time. We can know the past but not the future, because knowledge is a form of information, and information processing follows the thermodynamic arrow. In reverse time regions, observers would know what we call the future but not what we call the past, because their information processing would follow their local thermodynamic arrow. The emergence of time's arrow from entropy also provides insights into the nature of physical law itself. The fundamental equations of physics describe possibilities and relationships, but they don't determine which possibilities actually occur or how relationships unfold in experience. The thermodynamic arrow provides the additional ingredient that transforms static mathematical relationships into dynamic experiential sequences. This suggests a hierarchy in physical law, with time-symmetric fundamental equations at the bottom and entropy-based temporal emergence at higher levels. The fundamental laws define what relationships are possible, while thermodynamics determines how these possibilities manifest in the experience of embedded observers like ourselves. The implications for cosmology are equally profound. If time's direction emerges from entropy gradients rather than being fundamentally built into space-time, then different regions of the universe or multiverse might have different temporal orientations. Some regions might have entropy increasing toward what we call the future. Others might have entropy increasing toward what we call the past. And still others might have more complex temporal structures with multiple or fluctuating directions. Such temporal diversity would be unobservable from our perspective because observation itself is an entropy-increasing process tied to our local temporal orientation. But it suggests that our experience of uniform temporal flow throughout the observable universe might be a selection effect rather than a fundamental property of reality. These ideas also connect to cutting-edge research in quantum gravity and the fundamental nature of space-time. Some theories suggest that space and time themselves might be emergent properties of more fundamental quantum information processing networks. In such models, both spatial extension and temporal flow would arise from underlying information theoretic processes rather than being fundamental aspects of reality. If these approaches prove correct, then time's direction might emerge from the organization and flow of quantum information at the most fundamental level of reality. The arrow of time would still be tied to entropy and information processing, but these concepts would apply to the quantum foundations of space-time itself, rather than just to macroscopic thermodynamic systems. Understanding time's direction as an emergent property also provides new perspectives on some of the deepest questions in physics and philosophy. Questions about the beginning and end of time, the nature of existence and non-existence, and the relationship between mathematics and physical reality all take on new dimensions when viewed through the lens of emergent temporality. Perhaps most remarkably, this analysis suggests that our direct subjective experience of temporal flow, far from being a mere illusion or epiphenomenon, might actually be one of the most fundamental aspects of reality. The flowing time that consciousness experiences might not be separate from the physical processes that support consciousness, but rather an integral part of how information processing systems like brains interact with the entropic structure of space-time. This deep connection between consciousness, information, entropy, and temporal experience points toward a synthesis of physics and philosophy that could transform our understanding of what it means to exist in time. The direction of time might not be just a feature of the physical world, but the very foundation that makes the experience of existence possible at all. After our comprehensive journey through the physics, mathematics, and philosophy of time reversal, we arrive at the moment of scientific judgment. What does the current state of human knowledge tell us about the possibility of time flowing backward? Can we provide a definitive answer to whether time reversal is real, possible, or merely a theoretical curiosity? The verdict that emerges from our investigation is both surprising and profound, revealing that time reversal is simultaneously impossible and inevitable, forbidden and fundamental. The scientific verdict begins with an unambiguous confirmation that time reversal is absolutely real at the most fundamental level of physics. This is not speculation or theory, but established experimental fact. The equations that govern the deepest laws of nature, from quantum mechanics to general relativity, demonstrate perfect time reversal symmetry. Every fundamental physical process that can occur in forward time can equally occur in backward time without violating any basic principle of physics. We have observed this symmetry directly in laboratory experiments. Quantum systems regularly demonstrate time reversal through quantum revival phenomena. Particle physics experiments at facilities like CERN have confirmed time reversal symmetry to extraordinary precision. Nuclear magnetic resonance systems have been made to evolve backward through time, retracing their quantum evolution with perfect fidelity. Optical systems have demonstrated electromagnetic time reversal using phase conjugation techniques. The fundamental time symmetry of physics is not just theoretical, but experimentally verified reality. Yet simultaneously, time reversal is effectively impossible at the macroscopic scales where we live our lives. The second law of thermodynamics creates an arrow of time so robust and universal that macroscopic time reversal, while not forbidden by fundamental physics, becomes so improbable as to be practically impossible. The probability of observing spontaneous entropy decrease in macroscopic systems is smaller than the probability of finding a specific atom in the observable universe by random chance. This creates a fascinating scientific paradox. Time reversal is perfectly allowed and regularly observed at microscopic scales, yet never occurs at macroscopic scales. The universe exhibits perfect time symmetry in its fundamental laws while displaying perfect time asymmetry in its large-scale behavior. This paradox reveals one of the deepest features of physical reality, the emergence of irreversible behavior from reversible laws. The resolution of this paradox lies in understanding that time reversal is fundamentally a question of scale and initial conditions rather than physical law. At microscopic scales, where systems involve small numbers of particles and can be isolated from their environments, time symmetry manifests naturally and observably. At macroscopic scales, where systems involve vast numbers of particles and cannot be isolated from thermal environments, statistical effects overwhelm the underlying time symmetry. But the scientific verdict goes deeper than just confirming time symmetry and thermodynamic irreversibility. Our investigation reveals that the very experience of temporal flow might be more subtle than previously understood. The direction of time that we experience so vividly might not be a fundamental feature of reality, but rather an emergent property of entropy gradients and information processing systems. This emergent view of time's arrow has profound implications for our understanding of consciousness, causality, and existence itself. If consciousness requires entropy, increasing information processing to function, then conscious observers can only exist in regions of space-time where thermodynamics creates a consistent temporal direction. This explains why all conscious beings in our observable universe experience the same direction of temporal flow, and why we cannot observe reverse time regions even if they exist. The scientific verdict also clarifies what time reversal would actually mean if it occurred. Contrary to science fiction portrayals, time reversal would not allow conscious beings to retain forward time memories while experiencing a backward time world. Instead, consciousness would reverse along with all other physical processes, making time reversal undetectable from the inside. If time reversed tomorrow, we would never know it happened because our memories and thought processes would reverse as well. This undetectability of time reversal from internal perspectives reveals something profound about the relationship between subjective experience and objective physical processes. Our sense of temporal flow might be less about detecting the actual direction of time and more about experiencing the accumulation of entropy in our information processing systems. Time might not flow at all in any objective sense, but consciousness creates the subjective impression of flow by navigating through the thermodynamic structure of space-time. The cosmological implications of our verdict are equally significant. The arrow of time we observe appears to be a consequence of the initial low entropy conditions established by the Big Bang, rather than a fundamental asymmetry in the laws of physics. This suggests that in other cosmic regions or other universes with different initial conditions, time might flow in different directions or might not have a well-defined direction at all. Yet we cannot observe such regions because observation itself is an entropy increasing process tied to our local thermodynamic arrow. This creates a kind of temporal horizon beyond which our forward time observation methods cannot penetrate. Reverse time regions might exist throughout the cosmos, but they would be as invisible to us as we would be to them, separated not by spatial distance, but by incompatible temporal orientations. The experimental verification of time reversal symmetry also provides crucial confirmation of our theoretical understanding of fundamental physics. The fact that laboratory demonstrations of time reversal match theoretical predictions with extraordinary precision validates our mathematical descriptions of nature's deepest laws. This gives us confidence that our understanding of time symmetry is correct, even when extended to scales and conditions far beyond direct experimental verification. However, the scientific verdict also acknowledges significant limitations in our current understanding. While we can demonstrate time reversal in carefully controlled quantum systems, we do not yet have the technology to create or observe time reversal in complex many-body systems. The gap between microscopic time symmetry and macroscopic irreversibility remains one of the most important areas of active research in physics. Future experiments may push the boundaries of observable time reversal to larger scales and more complex systems. Advances in quantum control, laser cooling, and information processing might eventually allow scientists to demonstrate entropy reduction and time reversal in systems containing thousands or millions of particles. Such experiments would provide crucial tests of our understanding of the relationship between microscopic symmetries and macroscopic irreversibility. The verdict also recognizes that some aspects of time reversal remain genuinely speculative. While we can be confident about time symmetry in fundamental physics and entropy-based irreversibility in macroscopic systems, scenarios involving cosmic-scale time reversal, such as Big Crunch-induced temporal flip or multiverse regions with reversed arrows, remain theoretical possibilities that await further experimental and observational confirmation. The implications for technology and engineering are already becoming apparent. Time reversal techniques developed from fundamental physics research are finding applications in medical imaging, acoustic focusing, seismic analysis, and optical communications. Understanding the principles of temporal symmetry is leading to new methods for correcting distortions, focusing energy, and processing information. These practical applications demonstrate that time reversal physics is not just abstract theory, but useful knowledge with real-world benefits. Perhaps most importantly, the scientific verdict reveals that questions about time reversal are fundamentally questions about the nature of existence itself. The direction of time is intimately connected to the possibility of complexity, consciousness, memory, and meaning. Understanding time reversal has illuminated the deep relationships between physics and philosophy, between objective physical processes and subjective conscious experience. The verdict also suggests that some of our most basic intuitions about time might need revision. The feeling that time flows forward might be more about the structure of memory and consciousness than about any objective temporal flow. The distinction between past and future might be less fundamental than the distinction between regions of increasing and decreasing entropy. The apparent impossibility of changing the past might be just as illusory as the apparent possibility of affecting the future. Looking toward the future of time reversal research, several exciting possibilities emerge. Quantum computers might eventually simulate time-reversed evolution of complex systems with perfect accuracy, allowing us to explore reverse time scenarios that remain beyond experimental reach. Advanced space-based observations might detect subtle signatures of reverse time regions in the cosmic microwave background or other cosmological data. Theoretical advances in quantum gravity might reveal how temporal symmetries emerge from even more fundamental quantum information structures. But regardless of future discoveries, the current scientific verdict on time reversal is clear and remarkable. Time reversal is both impossible and inevitable, both observed and unobservable, both fundamental and emergent. It represents one of the deepest symmetries of nature while being responsible for one of the most obvious asymmetries of experience. It is allowed by the most basic laws of physics, while being prohibited by the most universal statistical principles. This paradoxical nature of time reversal reflects the profound strangeness of reality itself when examined at its deepest levels. The universe operates according to principles that are simultaneously simple and complex, symmetric and asymmetric, deterministic and statistical. Time reversal embodies all of these paradoxes, making it one of the most revealing windows into the fundamental nature of existence. The final scientific verdict is that time reversal is real, observable, and fundamental to our understanding of physics, while simultaneously being practically impossible, experientially undetectable, and cosmically rare. This verdict challenges us to expand our conception of what is possible in nature, while deepening our appreciation for the remarkable conditions that make our forward time experience possible. Understanding time reversal ultimately teaches us that reality is far stranger, more subtle, and more wonderful than our everyday experience suggests. The direction of time that seems so fundamental to our existence emerges from deeper symmetries and statistical principles that operate on scales, from the quantum to the cosmic. We live in a universe where time can flow backward, even though we can never experience it doing so. We began this journey with a simple question that seemed almost absurd. What if time flowed backward? What started as a thought experiment has taken us through some of the deepest territories in all of science. From the quantum foundations of reality to the cosmic evolution of the universe, from the nature of consciousness to the meaning of existence itself. The answer we've discovered is far more profound and beautiful than we could have imagined when we first asked whether time could reverse its flow. Time reversal, we now understand, is not impossible. It is woven into the very fabric of physical law, embedded in the fundamental equations that govern everything, from subatomic particles to the curvature of space-time itself. Every process that occurs in our forward time universe could, in principle, occur in perfect reverse, without violating a single law of physics. The universe could run backward just as easily as it runs forward, and the mathematical descriptions of nature would remain completely valid. Yet this fundamental possibility remains forever hidden from our direct experience. The arrow of time that we feel so deeply, that gives structure to our memories and meaning to our actions, emerges not from the laws of physics, but from the statistical inevitability of entropy increase. We live in a universe that began in an extraordinarily organized state and has been evolving toward disorder ever since. This thermodynamic arrow creates the temporal orientation that makes consciousness, memory, and life itself possible. The profound insight that has emerged from our exploration is that the direction of time is neither purely fundamental nor purely illusory. It is emergent. Like the wetness of water emerging from the behavior of H2O molecules, or the temperature of a gas emerging from the motion of countless atoms, the arrow of time emerges from the statistical behavior of vast numbers of particles following time-symmetric laws. This emergence is real and consequential, even though it arises from deeper symmetries. This emergent nature of time's arrow reveals something beautiful about the relationship between simplicity and complexity in nature. The universe operates according to elegantly simple time-symmetric laws at its foundation, yet these same laws give rise to the rich temporal complexity we experience in our daily lives. The forward flow of time, with all its associations of growth, learning, aging, and change, emerges naturally from underlying principles that treat all temporal directions equally. Perhaps most remarkably, our investigation has revealed that consciousness and the arrow of time are intimately connected. We don't simply observe time's flow, we participate in creating it through the entropy-increasing processes of thought, memory formation, and decision-making. Our subjective experience of temporal passage is not separate from the physical processes that generate the thermodynamic arrow, but is actually one of the ways that entropy increase manifests in the universe. This deep connection between mind and time suggests that consciousness is not an accidental byproduct of physical evolution, but rather a natural expression of the same thermodynamic principles that create temporal direction throughout the cosmos. We are not observers standing outside the flow of time, but participants embedded within it. Our very existence dependent on the entropy gradients that make temporal experience possible. The journey through time reversal has also illuminated the remarkable nature of the universe we inhabit. The fact that we can ask questions about time reversal, conduct experiments to test temporal symmetry, and develop mathematical theories that describe both forward and backward time evolution reveals something extraordinary about the relationship between mind and cosmos. We are patterns of organized matter and energy that have become capable of understanding the laws that govern our own existence. This understanding carries with it a sense of cosmic responsibility. If consciousness and time's arrow are connected as deeply as our investigation suggests, then the thoughts we think, the memories we form, and the decisions we make are not just personal psychological events, but contributions to the ongoing increase of entropy that drives the arrow of time forward. In a very real sense, consciousness participates in the creation of temporal reality. The exploration of time reversal has also revealed the limits of human knowledge and experience. There may be regions of space-time where entropy decreases and time flows backward relative to our experience, but these regions remain forever beyond our observational reach. There may be forms of consciousness that operate on entropy, decreasing principles completely alien to our understanding. There may be universes where temporal relationships are far more complex than anything we can currently imagine. These limitations remind us that science is an ongoing journey rather than a completed destination. Each answer we discover opens new questions. Each mystery we solve reveals deeper mysteries. The investigation of time reversal has solved some puzzles about the nature of temporal experience, while simultaneously revealing how much we still don't understand about the relationship between time, consciousness, and reality. Yet the journey has also demonstrated the extraordinary power of human reason and scientific investigation. Starting from pure thought experiments about reverse time flow, we have been able to make precise experimental tests, confirm theoretical predictions, and develop practical technologies. The same intellectual tools that allow us to imagine time flowing backward also allow us to understand why it flows forward, and what this means for our place in the cosmos. The practical implications of understanding time reversal extend far beyond academic curiosity. The technologies emerging from time reversal research are already improving medical imaging, enabling new forms of acoustic focusing, and advancing our capabilities in optical communications. Understanding the principles of temporal symmetry is leading to innovations that enhance human life and expand our technological capabilities. But perhaps the most important implications are philosophical and existential. Understanding time reversal changes how we think about causality, free will, and the nature of existence. If the flow of time emerges from entropy, rather than being fundamentally built into reality, then our relationship to past and future becomes more subtle and complex than traditional conceptions suggest. We are not simply carried along by an objective, temporal current, but are active participants in the entropic processes that create the experience of temporal flow. This perspective offers a new way of understanding human agency and responsibility. While we cannot change the past or control all aspects of the future, we can recognize our role as entropy-increasing information processing systems that contribute to the ongoing creation of temporal structure. Our choices and actions are part of the thermodynamic processes that drive the arrow of time forward, making us participants in the fundamental dynamics of reality rather than passive observers of predetermined events. The investigation of time reversal also provides a profound perspective on the temporary nature of our existence. Individual human lives represent brief local decreases in entropy, temporary islands of organization in the vast sea of cosmic entropy increase. We exist because the universe provides sufficient energy gradients to power the complex information processing systems that constitute consciousness. But these gradients are gradually dissipating as entropy increases. Yet this temporary nature need not be cause for despair. Instead, it reveals the remarkable improbability and preciousness of conscious existence. The fact that patterns of matter and energy can become organized enough to understand their own existence, even temporarily, represents one of the most extraordinary phenomena in the known universe. We are the universe becoming conscious of itself, even if only briefly. The arrow of time that defines our reality also defines our opportunities and responsibilities. Because entropy increase creates the possibility of complexity, growth, and learning, the forward flow of time opens up possibilities for understanding, creativity, and meaning that would not exist in a static or randomly fluctuating temporal environment. The direction of time creates the arena in which consciousness can develop, flourish, and discover its own nature. Looking toward the future, our understanding of time reversal will undoubtedly continue to evolve. New experiments will probe the boundaries between microscopic time symmetry and macroscopic irreversibility. Advanced theoretical work will explore the quantum foundations of temporal experience. Space-based observations may detect subtle signatures of exotic temporal phenomena in the cosmic background radiation. Each advance will deepen our understanding of time while revealing new mysteries to explore. But regardless of future discoveries, the central insights from our exploration of time reversal will remain. Time's arrow is real and consequential, even though it emerges from deeper symmetries. Consciousness and temporal direction are intimately connected through the thermodynamic processes that make information processing possible. The universe we inhabit represents an extraordinary set of conditions that allow for the emergence of complexity, understanding, and meaning. Perhaps most importantly, we have learned that asking deep questions about the nature of time leads inevitably to deep questions about the nature of existence itself. Time reversal is not just a physics problem, but a window into the fundamental relationship between mind and cosmos, between the mathematical structures that describe reality and the conscious experience of living within that reality. The arrow of time that seemed so simple and obvious when we began our journey has revealed itself to be one of the most profound and mysterious aspects of existence. It emerges from the interplay between fundamental symmetries and statistical inevitabilities, between microscopic laws and macroscopic phenomena, between physical processes and conscious experience. This arrow defines not just the direction of temporal flow, but the very possibility of existence as we know it. In the end, understanding time reversal teaches us that we live in a universe far stranger and more wonderful than everyday experience suggests. Time can flow backward, even though we can never experience it doing so. The direction of temporal flow that seems so fundamental to our existence is actually an emergent property of entropy gradients and information processing. Consciousness and time's arrow arise together from the same thermodynamic principles that govern the evolution of the entire cosmos. The arrow of time is not just a feature of the universe we observe, but the very foundation that makes observation, understanding, and existence possible. It is the arrow that defines reality itself.